for the introduction, and thanks to the organizers for inviting me. It's great to be in Vienna, and I apologize to the French delegation that this remains a Beamer presentation and not a Blackboard talk. There was a lot of pressure, but yeah. I see. So, okay, I will start with kind of giving an outline of the field of shrinking targets problems, which kind of seek to understand the recurrence behavior of typical orbits in dynamical systems. And those problems can be stated in very broad generality. I mean, you can be in the abstract setting of a probability space and a measure-preserving transformation. And then you look at a sequence of subsets which shrinks to, whose measure shrinks to zero as m goes to infinity. And we call that a sequence of shrinking targets. And such a sequence is called nested if the next element in the sequence is contained within the previous one. And so, of course, very often we will consider a sequence of balls centered around a fixed center x0. And then the classical shrinking target problem considers the set of infinitely many hits. So we consider those points x, where for a sequence of shrinking targets Bm, the nth iterate lies in the nth target set for infinitely many times n. And this can be expressed as a lim subset, if this sequence of targets is nested, then this set of infinitely often hitting points is a T-invariant set. And give you that proof so that we have one proof in this talk at least, and then hopefully for the main results at least some ideas of the proof. So by definition of when a point x lies in this set of infinitely many hits, then by the definition we have this Dn of x lies in Dn for infinitely many n. And now we write this nth iterate as the n minus first image of the point T of x. And here on the right-hand side, we exploit the fact that our sequence of shrinking targets is nested. So now we see that for this point T of x, we have infinitely many times where the iterate lies in the corresponding target set. So our point T of x lies in the set of infinitely many hits, and so x lies in the preimage of it. So we have this inclusion here, and then by exploiting that T is a measure-preserving transformation, we see that they can differ in a null set at most, and so our set of infinitely many hitting points is a T-invariant set. And so for ergodic transformation T, we get the 0-1 law, namely that the measure of the infinitely often hitting points is either 0 or full measure 1. And of course, you now try to find conditions on the decay rate of these measures for our target set, so that we can either measure 0 or measure 1 for our infinitely often hitting. And as I mentioned, this set is a lim subset, so it's kind of natural to look at the Borel-Cantelli lemma from probability theory. So where if we have a sequence of events and the sum of the measures converges, then the measure of the lim subset is 0. And that part we can immediately apply on where we take as the set as these events the nth preimage of our nth target set, and then by the fact that our transformation T is measure preserving, the measure of this event En is exactly the measure of the target Bn. So our if this the sum of the measures converges. This corresponds exactly to the situation then that the measure of the event, sum of the measures of the event converges, so the lim subset has measure 0. So in our case, the set of infinitely many hits has measure 0. So for the second part of the Borel-Cantelli lemma, of course, the application is not clear at all, because the probabilistic version, we require pairwise independence of the events. And yeah, this is certainly not fulfilled in our settings, because yeah, our events En kind of are linked to each other via the dynamics of the transformation T. But we speak about so-called dynamical Borel-Cantelli lemmas if also the second part of the Borel-Cantelli lemma holds true, namely if the divergence of the sum of the measures gives you that the set of infinitely many hits has measure 1. Say that the transformation T satisfies a dynamical Borel-Cantelli lemma for a given family of nested targets if yeah, we have this dichotomy condition. And yeah, typically we, as this sequence of targets, we consider sequence of balls around a fixed center where the radius shrinks to 0. And if a dynamical system has a dynamical Borel-Cantelli lemma for all such sequences of balls, then one often says that this dynamical system has a monotone shrinking target property. And yeah, the monotone shrinking target property has been verified for a long list of dynamical systems. I mentioned some of them, and I apologize to all people whose results I have not mentioned here. I mean, it's a very long list. No, it's not me. It's not my first result. No. But yeah, so the Walter Philipp, he had results on expanding maps on the interval and the Gauss map. And yeah, maybe let me also highlight the work of Kleinburg and Margulis. Because, okay, on the one hand, it's always good to mention that Margulis worked on a subject, because it gives a lot of credibility to the field and significance. But I mean, their work is certainly great, because it had important applications between geometry and number theory, and gave a new proof of Khinchin's theorem on simultaneous Diophantine approximation. And yeah, but so yeah, it's a long list of different types of system where the monotone shrinking target property could be verified. And of course, the general idea is to use the mixing property as a replacement for independence from probability theory. But yeah, just mixing is not good enough. So there is Bayat constructed a counterexample of a mixing diffeomorphism without the monotone shrinking target property. So you need a kind of sufficient decay of correlation, let's say, so to play the game of getting the dynamical Borel-Cantelli lemma. It is a kind of a reparameterization of a linear toral flow with a complicated reparameterization function. So it's really manufactured to give you a counterexample. So it's not. Yes, it comes from basically you take a linear flow on the torus, but then you take a reparameterization that is designed to fail this. But yes. And it has a very slow decay of correlation. And so then there are follow-up works by Galatolo and so on, and they then try to get higher decay of correlation, but and still keep this as a counterexample. So yeah, kind of at the edge to maybe get optimal, or in the sense, okay, where does it break, or if there's some kind of general point for the decay of correlation where you get the monotone shrinking target. Yes, I think they are easier, but so Fayyad's one is quite involved. All right. So yeah, after this work on the classical shrinking target problem, I want to consider a stronger notion, namely what is called eventually always hitting points. So this terminology was coined by Dubik-Kelmer, although the concept itself has already been investigated earlier. But okay, so this set of eventually always hitting points, these are those points x, where there exists a point of time n, such that after this point of time n, you always have a hit with your mth target within your orbit segment of length m. So within your first m iterates, you always have to lie or have to hit the mth target at least once. So kind of, okay, intuitively to be eventually always hitting points, you either hit the center very close and then you can allow yourself to wander around and sometime elsewhere, but then you have to come back with another very close hit to the center, or you kind of hit your or you come somewhat close to the center frequently. So these are kind of the two main mechanisms to become a eventually always hitting point. And to kind of compare or motivate this this notion of these eventually always hitting points, one can also look at the Diophantine approximation, where we also have these two versions, namely on the one hand what's called uniform Diophantine approximation, or sometimes Dirichlet's theorem, namely that yeah, for any alpha and m, there exists a q between 1 and m such that this distance is less than 1 over m. And compared to the kind of asymptotic Diophantine approximation, or sometimes this is a more famous version of Dirichlet result, namely that for any alpha, there exists infinitely many q such that I get 1 over q closeness. So this kind of stronger version here that corresponds exactly to our eventually always hitting point scenario, while here we have the infinitely many hits. As for the classical shrinking target problem, we can also express this set of eventually always hitting in set theoretic notation. And this time it turns out to be a lim-inf set. So here, since we look at the first m iterates, we take here the union over the first m pre-images of our target Bm. And then since we want to have a hit after this point of time n, we have to take here the union over all m after n. And so, yeah, in the end, we get this lim-inf set here. And yeah, this compared to the situation of the classical shrinking target problem with a lim subset, this makes the analysis actually much harder and more complicated. But still, the kind of can formulate such a shrinking target problem for this new notion of eventually always hitting points. And so I mentioned that this is a stronger notion or a stronger concept in the sense that if we ignore those points that hit the center of our sequence of target once, I mean, if you hit the center once, then you don't need a future hit anymore because this hit will be in all your target sequences for all future times. But apart, if you ignore those points, and this is exactly this set lambda here, and then the set of eventually always hitting points is contained in the set of infinitely many hits. But this set lambda, since our sequences of measures go to 0, this is a null set. So kind of up to this null set, we really have a stronger property. And then with the same proof as the one for the infinitely often hitting points, one can show that this is a T-invariant set. And so again, for ergodic maps, we get a 0-1 law. And you can ask the question again, so under what conditions on the decay rate of our measures of the targets do we get measure 0 or full measure 1? And yeah, we started that investigation with Thomas and Maxime Kirsebaum. And in our first paper, we got kind of results that applied in quite some broad generality, but they were not that tight conditions, let's say. But let me just kind of summarize those for the moment. And so the kind of to find sufficient conditions for the set of eventually always hitting points to be of measure 0, we can formulate those sufficient conditions for all transformations that have kind of hitting time distribution in the following sense, namely, okay, we have already seen in other talks the hitting time function here, and as long as we kind of then we define for a sequence of our target set Bm this function over here, and as long as this one is bounded away from 1 for all times t, we get the following sufficient condition for the set of eventually always hitting points to be a null set, namely if there is a constant c such that the measure of our target set is bounded by constant over m, then the set of eventually always hitting points has measure 0. In particular, you see that this is quite different from the situation for infinitely often hitting points because, yeah, the sum over constant over m diverges. So for hitting infinitely often, you had full measure, while here we get measure 0. And yeah, of course, this holds true for all systems that have kind of hitting time statistics. Yeah. So in the other direction, namely to find sufficient conditions for the measure of eventually always hitting points to be a set of full measure, yeah, we place that in the framework of sufficient decay of correlation, or kind of dependent on the decay, on the speed of decay of correlation. So where we consider decay of correlation between L1 and functions of bounded variations, and kind of dependent on the decay rate here, we kind of get different conditions on the decay rate of the target sets. So yeah, no worries, this won't be part of a test or an exam later. It just shows that kind of dependent on the speed of decay of correlations, we got different results on the decay rate of the measures to guarantee that eventually always hitting points had full measure 1. And so let me kind of show you a situation for some toy examples. So if we consider the doubling map, then we kind of really had this gap here between, okay, if it was constant over m, then eventually always hitting points had measure 0, while if we have measure at least constant times logarithm m square over m, then we got full measure 1. So there is quite a gap between these conditions. At the same time, although then the paper appeared in print way later, but the preprint appeared just a couple of weeks after our work. There was a parallel work by Kleinberg, Konstantinos, Richter, and so they got tighter conditions, but their results typically only worked for very specific sets of targets. And so kind of to phrase their results, yeah, we have to view it as a shift space, and then if we have as a sequence of targets, this sequence of cylinders here, then they got this quite tight condition, but it is still not a dichotomy result, because you still have the fluctuations of your sequence of the measures, and then yeah, they couldn't make a statement on measure of the eventually always hitting points. So yeah, so the question arose, okay, find a dichotomy condition for this measure of eventually always hitting points. And yeah, I mean, for a long time, actually, we didn't have a good idea how such a dichotomy condition should look like. But then, fortunately, Mark Holland entered the scene, and kind of it proved very crucial and useful to rewrite it to an extreme value theory question, or follow this extreme value theory approach that we have also seen in a couple of talks at this conference, namely to rewrite it using such a function psi that is decreasing and goes up to infinity as we approach 0. So yeah, as we've seen, you can take 1 over y or negative logarithm of y. And then we define for a fixed center x tilde, we define the observable phi of x via this function psi and the distance of x to this center x tilde. And then we consider the stochastic process defined via these observations and its associated maximum process. And then known that the kind of the set of points x, where the nth iterate lies in our nth target set, that corresponds to the event that the observation xn exceeds un, where un is the value that corresponds to the radius Rn under our function psi. And then, yeah, the maximum event corresponds to the event of the intersection over these sets xk less than un. Then we can rewrite our set of eventually always sitting points here. Yeah, this was a definition of the eventually always sitting points. And yeah, now this situation here that we are in the pre-images of this BM that corresponds to observation xk larger than un. And so we get that eventually said that mm is larger than un. So we are in the framework of statistical extreme value theory, and that kind of proved useful to already get the idea of, okay, what should a dichotomy condition look like? So as you have seen in this conference, you know that there are kind of two main questions maybe that you can ask on. On the one hand, you can ask for convergence in distribution. And what we will focus on today is then, or in this talk, is kind of on the almost sure growth rate of our maximum process Mn. So we want to find optimal bounding sequences such that almost surely our maximum process lies between these two sequences, Vn and Un. And so that we almost surely our maximum process is bounded by these two. That way, then we want to find also our dichotomy condition for this set of eventually always hitting points, where we, as we have seen, that can be rewritten as this, that the maximum process is larger than un. Okay, and so then, there are these so-called Robin-Siegmund series criteria or IID processes, which give you such optimal bounding sequences. Namely, okay, if we are in the setting of an IID process with a probability measure P, and we have a non-decreasing sequence UN, where the probability of the event x1 larger than UN goes to 0, and this n times this probability going to infinity, then we have the following dichotomy condition, namely dependent on the convergence or divergence of these series here, we get that the Mn larger than Un eventually has either measure 1 or measure 0. So kind of for our dynamical application in mind on the eventually always sitting points, then recall that, yeah, the probability of x1 larger than Un corresponds to the measure of the nth target set, where the radius Rn is linked to this to the Un via our function psi. And yeah, the probability of the maximum eventually larger than Un corresponds to the measure of our set of eventually always sitting points. And then, yeah, in joint work with Mark Holland, Maxim Kirsebaum, and Thomas, we could kind of find the dynamical analog of the Robin-Zsigmond series criteria in a dynamical setting. And let me state the result for piecewise expanding interval maps with an ergodic measure, which is absolutely continuous with respect to the Lebesgue measure. So this is kind of in parallel, if you recall this long list of shrinking target problem results that I showed you at the beginning. It was also started with Walter Phillips' results on the piecewise expanding interval maps. And we kind of, yeah, if you look at that long list, we are just on the top of that one, but still a long way to go. Yeah, so in that setting, if we consider this setting as described before with this observable phi, and yeah, then we have the analogous condition as in the Robin-Zsigmond series criteria on the sequences, or yeah, n times the measure of our target set, that this one is non-decreasing. And then, yeah, we have this technical condition here, which is, in reality, it's very mild because, I mean, since we will always ask for this sum of the measures to diverge, so that this condition does not hold would only be the case if we had a very weird measure with similarity in the density. But so usually I would have not mentioned this condition to you, but since my co-author is here and he would have called me out on that, I mentioned it, or maybe not. No, I hope that you would have forgotten about it, but I guess. So, but okay, apart from this technical additional assumption, which is quite mild, then we get the kind of dichotomy condition that parallels the Robin-Zsigmond series criteria, namely dependent on the convergence or divergence of this sum here, we yeah, get that our eventually always sitting points have measure 1 or 0. Okay. So, and yeah, to give you another application in number theory of our result and kind of for the Gauss map that you know. So if we have the Gauss map with the Gauss measure, then and we take as the observable exactly the 1 over x and then the integer part of this, then and we consider targets with a center around 0, then kind of these observations under our iterates of the Gauss map correspond exactly to the coefficients in the continued fraction expansion of the number x. And so then our kind of result gives us a result on the almost sure growth rates of those coefficients in the continued fraction expansion, namely kind of that for almost every x, their coefficients grow with this speed over n over log n. Yes, so I mean, we can definitely recover this result by Walter Philipp, and then you could add another log n plus constant log n. Okay. So yeah, since we have also heard Megan's talk about clustering and so on, we also have a dynamical version of those results. So if we recall that a cluster here referred to a kind of consecutive occurrences of an exceedance of a given threshold, and kind of also saw the definition of the extremal index, which is kind of the value of theta between 0 and 1, such that we have an extreme value law for our maximum process Mn, that we actually get here the convergence of the distribution with e to the power negative theta times t. And where then this extremal index theta kind of quantifies the intensity of clustering. So if theta is 1, then we get here our exponential distribution. So basically that has corresponds to the situation of no memory, while small values of theta correspond to the situation of long memory in the process. So kind of, and this 1 over theta can be seen as a kind of size of the clusters. And in dynamics, such a non-trivial extremal index can happen for a sequence of shrinking targets limiting onto a periodic point. Also seen that in Megan's talk, namely if we have a x tilde, a q periodic point of a transformation T, and again we take our observable phi linked to the distance to this periodic point x tilde as this function psi, then if you define the following events, un corresponds to x1 larger than un, and here we take those points that do not return to our target, nth target, within the first q iterates. So this is the set A and Q here on the right-hand side, so that for the first q iterates, we are not coming back to un. And then this proportion of the measure of A and Q compared to the measure of un, this can be used as an approximation to the extremal index. And of course, it gives a kind of proportion of points that do not return within the first q iterates. And when the limit of this theta exists, then this constant theta kind of takes the role of an extremal index in our extreme value law. And for example, if we have a hyperbolic repelling q periodic point for a piecewise expanding map and with a Lebesgue measure, then the formula gives us 1 minus 1 over the derivative of the q's iterate function. So if you kind of have a large derivative here, so it's kind of very repelling, say, then you get small value here, so your value here is close to 1. Because there is a small proportion that comes back after this q iterates. Okay, in that situation, we can also get a new kind of dichotomy condition, or a new situation. So if we are again in this situation of a piecewise expanding interval map with an ergodic measure absolutely continuous with respect to Lebesgue, and we can consider our observable by this function psi and the distance to now this periodic point tilde. That is hyperbolic periodic point of period q and finite derivative. Then we consider the sequence of balls that shrink towards that periodic point. And if we have a sufficient speed of this convergence of these approximations theta n towards theta, then we get a new dichotomy condition that includes here this extremal index theta. And now on this extremal index theta, the convergence or divergence of that series gives you whether the set of eventually always hitting points has measure 1 or 0, or in the extreme value theory terminology gives you the growth rate, the almost sure growth rates of that maximum process. Yeah, dependent on that extremal index. So this kind of, as far as we know, this was kind of the first appearance of this kind of new dichotomy condition in general, even in probability theory. I mean, of course, then we could construct some simple examples, but I think it's still open to kind of start a broader investigation on dependencies of this extremal index and this Robin-Zsigmond series criteria or variants of it. Okay. How much time do I have? Okay, I have some time to give you kind of the ideas or outlines of the proof. Of course, a lot of the idea is based on the fact that we want to take the proof of this Robin-Zsigmond series criteria from probability theory and carry it over to our dynamical setting using decay of correlation estimates. And for that one, a crucial tool was kind of Collet's blocking argument. And no worries, so the first part are assumptions on the decay of correlations, where we will then need exponential decay of correlations for bounded variation versus infinity functions. And then we also have to impose these short return time estimates. And okay, no worries that again, the conditions on this sigma will not be part of the exam at dinner tonight, but it's kind of, it just should show that this was kind of a involved argument, and kind of course, these conditions on the sigma change with every iteration of paper going between the authors. But I think in the end it is correct. So kind of, to show you, okay, that part was kind of tricky and technical, but and that it is not too simplistic what I will show you now. Because the rest, of course, then as I mentioned, crucial was Collet's blocking argument, where you, okay, we want to make a statement on this maximum process Mn. And so get a statement here. If we look at our time interval up to n, then what Collet's blocking argument suggests to do is to say, okay, we divide this into a couple of blocks where we have some length of the block is called p, and that is of the order n to the power s, where s is less than 1. And then between the different blocks, you have some gap t, and that one is of the order logarithm of n. So now you know why I gave a Beamer presentation, so that you don't have to read my handwriting. But then, yeah, you have these different blocks here, always with the gap t in between, and so on. And then we call this number of blocks q. So there are q blocks of length p separated by t numbers. And then kind of the vague idea is, of course, for this this length t of the order logarithm of n is used that we can exploit our exponential decay of correlation to basically get independence between these blocks of length p. And on these blocks of length p, we exploit this short return time estimates, namely that this, the sum of the measures of these returns within the first Pn iterates is kind of under control. And and kind of to keep this control of the correct order, yeah, we had to impose these conditions or this interplay between the different parameters. But yeah, this is kind of the vague idea of the kind of how we exploited then this Collet blocking argument. And in general, kind of to phrase that, or if I want to state it in the more general framework, to see how far what generality our result holds, we can state it for the situation of a conformal measure where so if we have an interval map, an ergodic probability measure, and that this measure is a Gibbs measure, which has a density with respect to a conformal measure, assumptions on the H is an eigenfunction of the transfer operator. We have a spectral gap. And here and that's why I stated the result earlier, just for the piecewise expanding interval maps with an absolutely continuous measure with respect to Lebesgue. So result Liverani, Sosol, Vianti show that these assumptions are hold for kind of broad class of piecewise expanding interval maps, and especially those with a Gibbs measure absolutely continuous with respect to that setting. We can kind of state our results. So if we have such a spectral gap statement and then our short return time estimate A2, of course that one then had to be verified in our setting for the piecewise expanding interval maps, then we can kind of find our dynamical version of the Rogman-Sigmund series criterion. So yeah, let me maybe focus for this talk now on the proof of the first part here a bit. Namely, so we want to find a result here on that eventually our sitting points have full measure 1, or that the Mn is eventually bounded from below by this psi of Rn. Then, yeah, from a dynamical Borel-Cantelli lemma, we get from the divergence of the measures of our targets here, of the sum of the measures of the targets, that for infinitely many times our xn will exceed un. So we exploit that. We know that the Borel-Cantelli, dynamical Borel-Cantelli lemma holds in our setting. So we get that infinitely many times xn will exceed un. So in particular, also our maximum process will exceed un infinitely many times, almost surely. So the Mn less than un eventually, that has measured here. So we can kind of express this set of the maximum process less than un infinitely many times. Yeah, we can just remove here this null set of eventually being less than un. Yeah? As I said, this is a null set, so if we remove it, we don't change the measure here. But now this set corresponds to the situation that infinitely many times your maximum process is less than un for time n, and then at the next time n plus 1, your maximum process has to exceed un plus 1. And of course, this situation corresponds to the situation that your n plus first observation had to exceed un plus 1. So, okay, we get this equality here, and we want to use this to prove then that, okay, this one has measure 0, and then hence Mn, at least un, eventually has full measure 1. And at this stage here, to exploit decay of correlation, we will actually, yeah, phrase it for some kind of L less than un, and our xm plus 1 larger than un, and then we choose ln carefully. That's less than n, but enough smaller than n, such that we can use some decay of correlation. We will kind of get a good approximation by taking here the product of maximum process less than u, and the next observation larger than u. And yeah, to estimate this part here, we will, as indicated here, exploit Collet's blocking argument to get an estimate on the measure of our maximum process less than u. Yeah, because, okay, so the fact that the maximum process is less than u, of course, that corresponds to the situation that all our xk are less than u. And this is contained if we go to a subset of times. And those subsets will be exactly here, the union over these blocks of length p. And yeah, so our subset here will consist of these q blocks of p consecutive numbers. And they are separated by t. And as I said, on this t, we will then use or exploit decay of correlation to get independence between these blocks of length p. And yeah, the measure on these blocks is approximated by 1 minus p times the measure of x1 larger than u. So we go to the complement and approximate the union over these complements by p times taking that, because we have the blocks of length p here. And yeah, then kind of trying to mimic independence between the blocks of length p, and we have q blocks. Kind of we will use this as an approximation of our measure of the maximum process less than u by taking these q blocks and the measure the blocks of length p. And yeah, then the exact form of the error that we do by this approach, that is kind of part of this Collet blocking proposition. And yeah, of course, also that one, on the first glance, it looks scary, horrible, and so on. But then in the end, I mean, it is exactly that, okay, we want to use this approximation between the maximum and taking these q blocks of length p independent from each other. So then, of course, we definitely lose here always these indices, set of indices here of length t. And I've also take into account then the inductively of the errors that we have done in the past. And that kind of are these expressions that show up here, that we kind of always have to take into account the errors that we have done for the earlier blocks. Then you can see here basically, okay, here we want then to use again a kind of decay of correlation argument to bound these error terms. And on this part here, we use our short return time assumption to bound those. But then in the end, get kind of a close approximation to an expression where kind of exploiting now this Robin-Zygmunt series condition will give us that basically their convergence will give us some ability of this set here. And by our first step, where we kind of said, okay, to express this one, it suffices to look at this one. So if we show some ability of those events, we get some ability of these events, and then hence can conclude that this is a set of measure 0. Thus, this eventually Mn will exceed Un almost surely. Okay, maybe let me stop at this point so that there is time for discussion.